So thank you very much for inviting me. And as you know, of course, we are connected through Toshi, and I've been following along the evolution from discussion to putting this forum together. And it's a great honor to be here and share some of the work we're doing. This is not a survey talk. This is more a talk about the work that we've been doing for the past 20 years, and as it relates to hopefully attacking things sooner than later. And as you know, when people talk about fusion, they always think 30 years. So I wanted to emphasize the idea of fast track, although I have to admit, as I just said, we're working on it for 20 years already. We're looking at a quite different way of doing that. And I wanted to introduce that. And this is maybe not as technical as some of the other presentations were, but I think it's sort of hopefully stimulating. And I mean, happy to expand in the written version with something that is more, technical in nature for the paper. But let me say first, this was a book that came out about 2 years ago now, I think it was. And in fact, I was listening to it in the car driving. I'm not time these days anymore to read things much other than the things that connect to what we do. And, he said, which almost made me lose my steering, said, we really need to clean up, we need to find a solution for clean energy and a switch to electric cars, some of the primary sources, of course, of carbon emissions in the world today. And it so happens that we're actually working by serendipity mainly on clean energy. But as you will see at the very end, I'll talk a little bit about what we're doing in the space of electric drivetrain and power management, power electronic solutions. So let me start talking a little bit, just very briefly, because I know most people covered this, just a slide on sort of the way we look at the future energy demand and what that tells us in terms of what kind of solution we're looking for. We've been thinking hard about this problem from day one, and this credit goes mostly to my PhD mentor back in the early 90s, late 80s, Norman Rostocker, who probably quite a few of you know. And Norman was obviously as much an insider in the development of fusion technology and plasma physics, as he was also critically looking at the end game and said the tokamak work, the stellarators, and the various others concepts may not be the best solution in the end when you look towards an applied end product in the utility space. And so this is what drove him and engaged me as a young PhD student back in 89 to begin working on this. And what started, frankly, as a thesis project evolved into now the largest privately funded fusion company. We're around for 20 years with about 250 people working for us. We have spent about $750 million, so $750 million in capital on this. It's become a much larger journey than I ever imagined it would be, but it's quite far along. And so I want to take you a little bit on a journey and share this with you, and then just give you a sense for what we've done, talk a little bit about some of the benefits that come as byproducts as you work on developing cutting edge technology. So to me, the way I look at this going forward, and these data sets are all more or less similar, right? We're looking at a doubling of the electricity demand out into the mid-century. We know that is in fact coming mostly from an increase in rising standards in the developing world. You can see here global population increases by about 20% or so. And so this, whether you look at electricity, like here, you look at total energy demand, those growth curves are about similar. And so we know that there's going to be a severe impact, in particular in the infrastructure starved part of the world, to bring electrification and meet the power demand. And so if you're looking at the sectors, I mean, electricity for electric use today makes up only a fraction of this. In fact, 70%, as most of you know, of course, this comes from transportation and a good major chunk from the industrial sector, smeltering, cement production, et cetera. And today in those areas, only about 6% is in the form of electric energy. But nonetheless, when you add all this up, it's clear that there's in the next couple of decades, there has to be a transformation. As we heard earlier today, I'm a big fan of Eric Regnault and the work that goes on in Earth System Science at UC Irvine. Anywhere you look, whether it's the ice melt or you look at the methane problem in sort of the polar circum region, it all points to us getting to a very peculiar situation that needs to fix soon. And so, just as the last speaker just said, nuclear energy is the only really carbon-free baseload, as we now call it, dispatchable source of power. And so if you're looking at that, the world is going to narrow in a choice that, is trying to use renewables where they fit, but it's going to need a complement. And that complement, I believe firmly, is going to be either fusion or fission or a combination of the two. And as we talked about fission a little bit, fusion doesn't suffer the long-lived radioisotope waste, et cetera, but it's got its other demons. It doesn't work today. So let me with that then switch and talk a little bit about what we're doing here and why I think fusion power makes sense. So first of all, if you look at criteria, what sustainable clean energy would look like in the context of the environment and the future growth of population. Ideally, we would want something that allows us the power to be made near the production center. So if you look at the world's urbanification, for instance, right, we have megacities now. Mostly they're along the coastlines. Some are very grown in a very organic, non-organized way when you think in some of the third world megacities. But in any case, while COVID maybe put a damper on people congregating, but in the long run, I think those trends are going to continue. And so if you think about power, the most efficient way without transmission line loss stuff, you make it right where you need it. And that means you need to have a certain safety margin built in. And that also then starts to exclude some of the renewables because those don't necessarily get their energy there. I mean, the wind may not blow where LA is, although we have sunshine here, but those kinds of things. Land use. Clearly, with more people and agricultural needs, et cetera, and the impact on the environment, just from a physical perspective, with transmission lines all over, vast areas covered by solar and wind, which obviously, because of low energy density, will need that footprint. Those are not ideal solutions either. As I said, transmission lines are a big thing. They are wasteful. They require space. They leave a big footprint in cost. So we want to minimize that. Clearly, carbon-free. If we can do this carbon-free and we can be free of long-lived nuclear waste, transmutation is certainly one way to try to get out of that jail card free. But on the other hand, fusion perhaps has something to offer here that does inherently not have short-lived waste. And then likely, of course, lastly, if we think about mining and the operations to get the fuels we're burning, reducing the impact on those natural resources in the ground and on the environment is also important. So looking a little bit more granular here, right? So in the case of fusion, of course, that exists in form of dispatchable power. It's reliable. It has, however, the long-lived demons of the radioactive waste. And of course, as we've seen in some of the nuclear accidents, there's a lot of potential for disaster when it runs away. And the problem is that the public today, I believe, when we look at this from an end product that we try to get into the utility sector and we need public acceptance, the public is very averse today. Certainly in the United States, I can say this loudly. This doesn't mean me, but it means the mass relatively uneducated that's seen a Fukushima or seen, a Chernobyl or something of that type and says, I don't want this in my backyard. Now, of course, gas and coal have supply issues, the variability in pricing. California is a great example. About 2 decades ago, when energy trading brought the state almost to bankruptcy. Those are big things, in addition, of course, to the carbon output. And then when you look at wind and solar, again, it's not quite affine to being put near the urban centers, and the variability is a problem as well. From a footprint perspective, we all know this, fusion is the highest energy density fuel. So if you look at this from a simplistic picture of what does it take to deploy a gigawatt of fusion power, well, you need less than a square mile of space, and you're many hundred times that in terms of a wind farm. And when you're looking at this from the perspective of what we're up against, right, today we're looking at a world, and if you talk to the people in the financial sector, they're all gung-ho on the reduction in solar prices and the reduction in prices of windmills. But today that makes about 12%. 80% of our power still comes in the form of fossil fuels, globally speaking. And so there's some areas that are a little bit more advanced, but this is sort of the average. And if I look at a future where most of that gap is made up now by renewable and non-carbon emitting sources, that's a tall order to fulfill. And again, against other constraints, this is a sophisticated problem. Yeah, I already covered this sort of the transmission line ideas. If you look at the US, it's a great case study, right? You have urban centers along the 2 coastlines. You have vast amounts of the interior with a lot of wind, for instance, Texas and the Central Plains, but you got to bring that power out to the coasts. And that is inherently costly and has other environmental impacts. And so fusion could be something, particularly a safe kind of fusion with non-radioactive emissions. And you can really put close to those to those consumption centers, and that would make a big difference. Footprint obvious, and fusion is a zero spec. We're looking here, and I'll talk about this in a little bit. We're looking at hydrogen boron with a stronger focus and interest than deuterium tritium for reasons that'll become apparent in a second. But it's clear that that's the direction we have to take. And when you look at the long rift versus the safety issues, that's again where I think fusion has a huge leg up if we can make it work. We clean, of course, it can be very safe. It will become very sustainable. There's essentially infinite fuel available. We're particularly interested in hydrogen boron. And that really was motivated by looking at the impact of neutrons and deuterium tritium neutrons in particular to the lifetime of the plant, and then the impacts to cost, to maintainability, to safeguarding a proliferation substance, not to even speak about breeding it and releasing to the groundwater and so on. And so the idea here to look at aneutronic fusion is something when you really look without care at the moment on the difficulty of the physics, so you want to do that, then that would be the ideal solution if you can make it work. And so this was one of the reasons that drove us to say, since most of the world in fusion is working on deuterium tritium, why not look at hydrogen boron as an option? And if you look at that reaction, it's marvelous. It produces essentially helium as a byproduct. Now, of course, there are parasitic site reactions that will make small amounts of beryllium, for instance, but these are mostly very short-lived isotopes measured, with half-lives in the tens of days or so. And then ultimately, of course, there is no irradiation zone around a plant like that. So it can really fit in with the idea of near an urban center. The other thing about hydrogen boron that's interesting, of course, is there's a lot to go around. You need very little to begin off. I mean, if you're looking at the scale of for instance, combustion-based gas turbine today, you're looking at something like a 500 megawatt installation. For a few hundred pounds or kilos of fuel, you could supply that facility with all its fuel for a year. So if you look at an infrastructure place like rural India, for instance, or Africa, how would you bring fuel there? You don't have pipelines, you don't have railroads for coal, et cetera, et cetera. You could do a helicopter dump of this kind of fuel, right? So this is quite exciting. And then, of course, it's ubiquitously distributed throughout the surface and in the crust and in the oceans. And today it's mostly used as a commodity product in laundry detergents and cleaning products and the like. And so there's no price volatility. There's no Saudi Arabia of boron, et cetera. It has all those geopolitical angles that cause us to get at war with each other also removed. So it's a quite interesting thing. What stands in its way, of course, is that it's inherently difficult to do, because you need, frankly, about the temperatures in the order of 3 billion degrees, or if you're looking in nuclear units, around 300, 320 keV. That's the total temperature in a system like that. And as you know, fusion is creeping up to the 10 keV point in tokamaks and what we're doing as well. And that's still a far cry of about a factor of 30 away where this would need to go. But when you look at it from a more holistic picture and you just don't focus only on the physics, which you have to, of course, but it's one aspect. And so again, to the holistic idea, begin with the end in mind. What would be an ideal reactor? Well, you want something that has technological readiness. So the aneutronic fuel takes out a lot of the materials challenges, little or no radioactivity, clean operational scenario, et cetera. So there's a long list I could list here, but these are some of the highlights. If you look in commercial viability, then you'll see this in a moment. We're thinking of a very compact machine. There is very little environmental impact. As I said, today, boron is mined by the metric ton. Either it gets out of seawater, or we have here very large deposits in the California deserts, for instance, where they just strip mine it off the surface. Maintenance is relatively straightforward. But of course, the physics. You need the high temperature. You need, therefore, an extremely efficient confinement, and you obviously need good stability. And so when we began thinking of this, we understood that those other two leaflets are in place, but the science is the hard kernel, and it's clearly where all the risk is. It's obviously the main risk in fusion today, but if you think about the deuterium-tritium fusion, by the time it meets success in ITER, for instance, or perhaps in a few other machines people are working on, public or private, even when you have deuterium-tritium burn with a Q or a net gain, greater than 1, you still need to manage the neutrons, the damage, the issues around proliferation, and all these other things I mentioned. So how can a private company get into this, right? I mean, first of all, when we looked at this, we said what private sector does well is efficiently deployment of capital. It wants to learn quickly. A beautiful thing in California is that we're not afraid to fail here. We have the Silicon Valley as a wonderful model. Fail fast is usually the synonym with which people think of things. And you want to try and error, and you want to develop things with lots of cycling opportunities so you can prototype, dismiss, go to the next thing. Partnership, clearly, as I said, we're about 250 people, but that's nothing. We have actually a very nice pool of talent globally now helping. There are traditional partners you would expect in the universities and the national lab. And in fact, our largest and most historically long and productive and deepest friendship is with the Butker lab in Novosibirsk, right? So we have a beautiful relationship there with their plasma physics and neutral beams people for decades now, developing and moving forward the state of the art on beams, and then as it plays into the work we do. and the work that they do on these mirror traps, for instance. But we've also tapped the private sector in the US. So for instance, Google is a component here. We're doing a lot of AI and machine learning work where it turns out that a lot of the innovations happening in the IT space are just as useful and applicable in the area of what we do. So we've deployed a large, particularly in the last 7-8 years, effort on machine learning and AI. And this goes into two vectors that I think are interesting. One is obviously to drive the reactor through a feedback control system. So in other words, you look for instabilities, you look for patterns you don't like, you teach it to the AI or the machine learning system, and then they counterbalance that with changing magnetic fields or changing the fuel rate injection or something like that. But the other thing we learned, and that was in a way almost as exciting, was operational optimization. And what I mean by that is again, back to cycles of learning. If you have an unknown terrain to go into with hundreds of parameters on one of these fusion machines, how do you make efficient headway to go from what you know today into the unknown as efficiently as you can? And when you think about us as a private company, we're under the gun of the investors. They write us a large check, they demand results, and if we don't, we're gone. And so it becomes very quickly a necessity of life to figure out how you can be really fast and predict in a way, how long is it going to take you to get from A to B? You need around 500 experiments. How can you make the learning rate as efficient as possible? And there's an interesting paper we wrote with Google a few years ago in Scientific Reports, where we showed a very interesting paradigm for high dimensional, sophisticated data sets with gaps and so on, how you can apply optimization. And what we also learned, which was interesting, that the combination of machine learning and AI and human intelligence, it creates an exponentiating function of fast learning. So it's the intuition of the person that's sitting at the control panel, the physicist, the engineer, together with the machine that can do all the number crunching. And so we've been deploying that very, very successfully. As I said, electronic fuel is a big deal because if you go into the depth of DT, you're dealing with long cycles of licensing patterns and things, whether it's the Nuclear Regulatory Commission in the US or say, for instance, ITER facing the French regulators. We know that those are very big delay components. And if you can avoid those to a degree, that'll help a lot. So not just is it good as an end product, but it's also on the way good to focus on it. As I said, private capital is a big deal. And then I'll come back to that at the end. There's now a whole bunch of spin-offs, just like when the space race happened and people were forced to develop esoteric new capabilities. Fusion drives you to innovate across a very large spectrum of technologies. So let me quickly cover what we do. So we work with a thing called an advanced beam-driven FRC core. So this is a very simple plasma topology, actually. It uses a solenoidal magnetic field. You can see there with these sort of blue coils here. And if you think about that being just a solenoidal field, say from left to right, when you inject enough of a current there, with plasma being a very good conductor, you can create its own magnetic field that superimposed creates a confining layer of closed field surfaces embedded in some mirror-like structure from the outside. And this is what we call in the field a high beta configuration. What that means is that this environment is dominated by the energy in the kinetic particles moving in the plasma, not as in tokamaks by the energy that's deployed and stored in the magnetic fields. That already tells you that it's going to be more efficient from a cost and an overall design perspective, because you can operate with lower fields, you need less sophisticated magnets, and you can do higher power density in the core, and so you can also shrink the system. So compact high power densities linked to that. It also allows you to work with aneutronic fuel for reasons that are perhaps a little too far afield here. This has to do with synchrotron radiation. And this kind of magnetic field has a very low field region in the center where most of the fuel peaks. And so you get less synchrotron radiation there. It also allows you to work with what we call large orbit particles. And so this was something that Norman brought in very early. And where that comes from is the idea that in accelerators, like CERN, for instance, we have very predictable capability to hold clouds of charged particles in magnetic topologies very efficiently. And in fusion, the typical lifetimes we're struggling with from an instability perspective, those are 10 to 100 microseconds or so for magnetohydrodynamic instabilities, for instance. And so it turns out that in tokamaks, this has been very nicely verified. If you inject energy particles that have a very much larger footprint in terms of their orbit size, they sample phase average a lot of the perturbations, and they become, not to say immune, but much better behaved. And that sort of anchors this plasma. And so we're injecting here tangentially here neutral beams at high energy that creates an additional layer of co-streaming particles of high energy that kind of improves stability and transport. And it's a simple geometry. And finally, and this is important, if you have to exhaust energy out of the system one day, in tokamaks, the exhaust systems, or as we call them, diverters, are the premium because they sit inside the magnetic cocoon. Here, you would actually have most of the emission products streaming out to the axial ends. And there you can have flaring magnetic fields. You use a large scale surface areas, so you can reduce heat loading on the wall, etc. And here's just some examples of particles here oscillating in these fields from simulations. So this is sort of what it looks like, what we have right now. This machine is about 2 double-decker buses in length. It produces fields up to about 3 kilogauss, which is sufficient here to get us up to temperatures of about 50, 60 million degrees, or somewhere in the neighborhood of 30 to 40 plus keV in total temperature. We're operating here also now, 33 to 4 keV in total temperature. We're also here operating at densities of about low to mid 10 to the 13 per cubic centimeter. So this is still about a factor of 5 or so less than where we need to go for a reactor, but it's in the reactor relevant regime already. And it works remarkably well. We actually make plasma into 2 end zones. We shoot this together in the center. We create this sort of hollow football that's rotating there. It's held by its own and the applied magnetic fields from the outside. And then we tangentially feed beams. And if you want to understand first order stability, it's like a spinning top. It's sort of an anti-aligned magnetic top in here and wants to perhaps flip. But if you give it enough rotation, which you can control through torquing from the injection of the neutral beams on the edge, we can control the rotation and we can hold these things very nicely stable. And in fact, feedback is an interplay between injection, frictional dissipation of too much over rotation, and then magnetic controls that basically position the thing and sort of keep it like almost like on a rigid axle.
5 minutes more. 5 minutes.
Thank you. So this is the progression of machines we built. We started in 1998 as a private company, raised friends and family money, and then migrated up to more sophisticated machines. Today we're operating the machine Norman here. That's our current prototype that we're working with. And as I said, this is fully in the collisionless regime. That means the physics that controls the plasma, that controls the instabilities and the turbulent transport is very much the same as the physics that controls the reactor state. So we're feeling very confident, and we can take this data and extrapolate forward. And we're now beginning construction of what I think is sort of our final must demonstrate machine, which is a machine we call Copernicus. We think we will have that operating sometime in the later 2023. And we think we will be able to show that we can get net energy on a device like that in the 24-25 timeframe. And then it becomes a process of developing a demonstration plan in the second half of the 20s, although we'll probably start work. We've actually started working, but really get going in parallel to Copernicus on the engineering of that. But the goal is by the late 20s to be ready to have a first sort of prototype machine running. And I think this is not fool's hope. There's still a lot of work. I don't want to sugarcoat this. There's a lot of risk, but we think can do this. Let me just give you here a very quick idea of how this, how we run. We store very efficiently energy inside of a very sophisticated power supply system. We run about typically 30 millisecond discharges on that. And these, frankly, are only limited by the energy storage. These are highly steady state configurations. They're very well, nicely tamed. We can ramp them up. You can see here plasma heating occurring. You can see field ramps. You see the fast ion accumulation as traced by the neutron rate. So we use today deuterium and deuterium and deuterium in the machine, or deuterium and hydrogen. And so there's some nice neutron tails that we can look at, and they'll give us a good idea. So this is a state that's quite different at tokamak. Here, everything is driven by most of the pressure of the particles is in fast ions with large orbits. It's a very high beta machine. Tokamaks operate like maybe 8% beta. We're more like 90+ % beta. And what's really beautiful, and we had predicted that, when you look at the leak rates and you look at the energy confinement time, it scales beautifully. And in fact, it's an older trace. We now go out to almost a keV in electron temperature, and it scales with the square of the temperature. So in other words, if you increase the temperature by 2, you get about 4 times the confinement performance. And this has to do with the accelerator physics that Norman and I expected to come in. And we've now clearly validated this across 3 machines. And we've done very sophisticated modeling with our academic friends in the US predominantly, and it all agrees. So this has a very good chance, we believe, to bootstrap us, not just to DT levels, which is about a factor of 2 or 3 beyond where we are today, but also higher up by another factor of 10 then to make perhaps PB11 workable. So this next machine is about a 10 keV machine, gets us roughly where ITER and the rest of the field is operating. By the way, though, not at tens of billion, but at $250 million capex. This is the beauty of this. So much more compact, quicker to build, quicker to iterate on, and hopefully something that will be able to give the world by the mid-20s to make a dent then into hopefully by the late decade and then into the 30s in terms of adoption of fusion. Let me just spend 1 minute here at the end on two topics that I think are interesting. The first one's on power management. So when we built Norman, we consume about 750 megawatts at peak power level to run the machine. And about the grid feed is about 2 to 3 megawatts. And so we had to figure out a buffering system that heretofore didn't exist that can, capacitively mostly store this power, release it reliably at these very high power flows into about 80,000 controlled parts. And so we developed a unique, think of it like an ant farm. Instead of moving a boulder with an elephant, you have a million ants, small modular power supplies. And when that worked beautifully, and today that runs with 100% uptime, the Fusion device, we said, can we deploy that elsewhere? And in fact, it turns out when you miniaturize it to the 10 to 100 kilowatt level, it can beautifully work in transportation. It can work in grid storage and buffering, peak shaving, power load shifting, et cetera. And there's sort of a connected ecosystem that in the end has clean fusion, hopefully in its center, or some carbon-free form of power, maybe small-scale fission or something the like. And then and around it, you have other decarbonization impacts from spin-off technology. And we're in fact now commercializing this. We actually signed our first licensing deal with one of the largest providers of utility scale mini and microgrids in the US. We're also in talks with some of the large tier one auto suppliers. And I think you'll very quickly see some of this fusion-derived technology in these other sectors. I think it's a very nice story. And let me close with something even further from home. This is an idea that we developed together with our colleagues at Butker. And this was taking these incredibly powerful neutral beams as fuel injectors for fusion and repurpose them as compact epithermal neutron sources for a technique called BNCT. If you Google it up, you will find it's a very interesting thing. It's been around for decades. It's the idea you inject the drug that brings boron 10 into a cancer cell. You irradiate it with low energy neutrons. The neutron gets swallowed by the boron 10, creates a mini fission event with a destruction radius of about the size of a cell. So you can locally disturb cancer cells without disturbing the healthy cells around it. The handicap with this has been that to date, they only could do these sorts of things on nuclear reactors. With these accelerator sources now that are uniquely capable by chance, what we developed fits perfectly for the low energy application. You can be very narrow band neutron sources. They can be very highly efficient. I'm happy to report that as we speak, we're just installing the first clinical system at a brand new cancer center in China. We have under contract now in the spin-off company orders from Europe, out of the UK and in Italy. And we just signed our first large US participant in the form of the Mayo Clinic, which is one of the largest clinical systems in the United States. So here's a spin-off that one wouldn't necessarily associate with fusion, right? Where you can take these things and bring them over. And because you developed esoteric technology performance, support fusion, you suddenly have something that can make a transformative impact on the rest of the quality of life. So let me close here. I know this was a whirlwind. I hope you got at least a hint of the idea. Be happy to expand more and further dialogue, and we'll share more as we write this in a written form. Thank you very much.
Thank you very much, Michko, for this very interesting talk. Actually, I would like to ask some short question regarding this therapy stuff. Yep. As I understand, there is the main problem there is not just not only the neutron source, but you need actually some drugs to deliver boron to the patient in quite targeted manner. Mm-hmm. Did you solve this problem in the United States or
Yeah, so this is a great question. So very quickly, I didn't have time in there to do this, but so today what's used is called boron phenylalanine. It's a very small molecule. It carries 1 boron per molecule. It's intravenously injected. It works through a larger amino acid uptake in cancer tissue. In other words, it has higher metabolic rate. So if you infuse it into the body, it will preferentially uptake there. To your point, you're absolutely correct. You can get best today between 3 and 5 enhancement in terms of the uptake into a tumor cell versus a healthy cell. And that's just because of the metabolic rate. Now, it turns out with that already, you can do treatments, and they've done. And in fact, this very drug, together with Sumitomo-based accelerators, the Japanese regulators, the Japanese FDA, last year, actually, in the spring, went from a stage 2 clinical trial to full approval. So in Japan, you can now, for head and neck cancers and glioblastomas soon, you can actually get treatments with this. So it works well enough. Yes, to your point, it has side effects. There is collateral damage. Now, to answer though the question on the drugs, so we actually developed over the last few years a spin-off in the pharma area working on this. And what we're doing, and this is actually beautiful, there's a lot of work in targeted chemotherapy. There's a lot of work in antibody technology, et cetera, right? And those are all looking to bring these toxic payloads into the body. And it turns out if you cleave those off and you create the chemical linker capability to the boron, which is inert to the body, it's an easier problem, it turns out. And we have, in fact, now in mice, in testing in our lab here in Santa Monica, almost 40-to-1 enrichment already. And this is using, in fact, cetuximab, which is a fairly standard used antibody that's out in various pharma products. So I think you will see, not immediately, I mean, by FDA clearance, but I think within the next 5 years, you will see a revolution. And we're on the forefront of that with our pharma development. New drugs that can do much better. They can load more boron in the tumor tissue, so you need less irradiation time, and it can be more precise. And I think there's a lot of other options. There's a whole host of cool stuff. With parties in Japan, we're working on passive targeting, where you can look at the vascularization of tumors with leaks. And if the molecules are small, they can leak through there, but they don't leak anywhere else. There's a lot of vectors to improve what we have. And I think this bears a lot of potential for people that today are basically sent home.
Thank you.